All right, everybody, class recording has started. So, on Friday, we introduced the idea of polyatomic ion, and I presented it to you something like this. So, here's oxygen with its 6 valence electrons. And so we know from our whole discussion about bonding, oxygen is looking to pick up 2 valence electrons, right, to get itself to 8. So, first thing that comes along is a hydrogen atom. And that hydrogen atom, being a nonmetal, is also looking to pick up electrons, right? So that's what nonmetals do. And, but we said that because it's a small atom, it only needs 2 valence electrons. And so this happens like this, and we get a covalent bond between that oxygen and that hydrogen because they're sharing that pair of electrons. And we can represent that then like this. All right. And now, hydrogen is good, but oxygen isn't, right? Oxygen is still looking to pick up another electron. If there was another hydrogen atom around, it would covalently bond with this oxygen, and we'd end up with water. But there isn't another hydrogen atom around. And the only other thing that's around, I think on Friday we did this, right? There's this sodium atom, right? And this sodium atom has this electron. And we know that sodium, being a metal, wants to get rid of that electron, right? Oxygen is still looking to pick up another electron, right? So we have this transfer like this. Oxygen picks this up, right? And now we end up with this, right? So, back when we talked about ionic bonding, we know now that sodium has a positive charge. It lost an electron, it's become a cation, right? Good. So that's positive charge. Because that oxygen has picked up that extra electron from sodium, it now has a negative charge. But it's already bonded to this hydrogen, and so now this group of atoms, this oxygen already bonded together with hydrogen, has a negative charge as a group. And so now we have this here, right? This is what we referred to as our polyatomic ion. Okay? Because it's a group of atoms. Some of them are covalently bonded together, but then it has to pick up another atom in order to get everybody to 8, right? That's the end goal. Everybody ends up with 8. Good? All right. So just a couple more examples. To help you sort of understand this, all right? So I'm just going to draw the whole thing together, and then I'll let you, then you guys can kind of see how it all gets together, all right? You don't even know I'm talking to you. Great. So, here, 3 oxygens and a chlorine. Okay? Does everybody have their 8 valence electrons based on this drawing? Right? Not everybody has their 8 valence electrons. Okay? These 4 atoms are bonded together, but there aren't enough electrons to go around for everybody to have 8. All right? What does this group of atoms have to do? How many electrons do they need to pick up as a group? 1, right? This chlorine, sorry, I didn't draw all of chlorine's electrons here. Sorry. Is that better? Does that make more sense? Okay, sorry. All right. So that chlorine on the far left, it's got its 6 electrons by itself, and then it's sharing those 2 with the next electron, the oxygen, right? The oxygen one in from the left, it's got 4 valence electrons, 2 on the top, 2 on the bottom, then it's sharing 2 pairs, right? One with chlorine and one with the oxygen, so on down the line. But this oxygen down here, right, only has 7. So it needs to pick up something somewhere else. If a hydrogen came along, it could covalently bond, all right? But, just like before, there's no hydrogen around. There's sodium with its 1 valence electron, all right? That 1 valence electron gets transferred over to here, right? And just like before, right, this sodium now has a positive charge of 1 plus, and this whole group of this whole group of atoms, right, until we added the green one, there was still exactly the same number of protons as there were electrons. We were just sharing, right? But now we added the green one, and that gives this a negative charge. This is a polyatomic ion. Why? Because it has more than one atom, and it has a different number of protons and electrons. In this case, more electrons than protons. Does that make sense? Okay. So, this polyatomic ion specifically, we call the chlorate ion. Let's connect that there so it looks like an A. This is the chlorate ion. Okay? The names are not something that you're going to be able to figure out on your own. Okay? So here's the deal. I won't make you memorize any of these polyatomic ions. All right? You'll have a chart on the test and when we're doing our things in class. Okay? But there's going to come a time whenever you take chemistry where you are going to have to memorize a list of polyatomic ions. Okay?
How many are there?
I mean, there's a bazillion of them, but you don't have to remember a bazillion of them. Okay? So one thing you have to remember is the name, and then you also have to remember the formula. So the formula for the chlorate ion is ClO3. Okay? But because it's an ion, what else do we need to know about it? What its charge is, right? So in this case, right, chlorate is ClO3 minus 1. Okay? That good? The one that we did here, right? I introduced this to you on Friday, I think. Okay? This is the hydroxide ion. Notice the ending is different than chlorate, hydroxide, right? There is a pattern, but it's not really obvious to see, so I'm not going to make you memorize that pattern. Okay? So for hydroxide, the formula, 1 oxygen, 1 hydrogen, right? But then what charge does it have? How many electrons did it pick up? Picked up 1 electron. Good there? Here's one more, just so you kind of see this pattern. All right? Nope. Here, here, here. All right? See if I can remember how to draw this. Okay. Messed it up. First thing I drew. All right? Okay. That's my Lewis structure for this group of atoms. Okay. All right. They're all connected. It's 4 atoms all connected to each other. Okay? CO3. Okay? But when you look up there, not every atom has 8 electrons, right? How many electrons short are we? We are 2 electrons short. Both of those oxygen atoms sort of coming off the bottom diagonally, neither one of them has 8. They both have 7. Okay? So in this case here, how many electrons is this group of atoms going to have to pick up? 2, right? We're going to have to fill this spot right here, and we're going to have to fill this spot right here. Okay? So this group of atoms, right, they're joined together by covalent bonds, but they have picked up some extra amount of electrons. Right? Does that make sense? Because that's a double bond, right? So how many electrons are they sharing there? They're sharing 4, right? Okay. So this one, CO3 minus 2, and we call this the carbonate ion. Okay. All right. Does that sort of make sense how these polyatomic ions come about? You okay with that? All right. I won't make you draw a picture like that, right? I'm just trying to show you how we get to these polyatomic ions. We have come up basically with, right, the end goal in any bonding situation is to end up with what? 8 valence electrons. Here, we are looking at different ways combining covalent and ionic bonding to get everybody what they need to get to. Okay? Good there? Okay? All right. So, let's talk about these formulas and these names. All right. So, we talked here, right? Nope. Ionic chemical bonds are compounds containing polyatomic ions. So, defining a polyatomic ion is a group of covalently bonded atoms that has a positive or negative charge and acts as one unit. I'm trying to show you that idea with those brackets, that those atoms are joined together. They act as a unit, all right, but they have a charge. And so we have to represent them as a unit, as a group, when they enter into these compounds, right? So here's a group of polyatomic ions. Let's move this down so you can see all of them, right? This is not all of them, but the couple we talked about, right? There's hydroxide, there's carbonate, chlorate didn't make this list, but it's one. It's also another one. Yes, Jeff?
Do these ions bond from another?
They can, but in order for, because they have gained charges, right? Now they're ions.
Yeah.
So what kind of ions bond together with each other? Oppositely charged ions, right? If you look at the vast majority of them, what charge do they have? Negative, right? There is one that does have a positive charge. This is the ammonium ion, and we'll look at that one a little bit later. So yes, it is possible that polyatomic ions can bond together with other polyatomic ions. It's just a matter of, right, we got to have positive and negative in order for that to happen. Okay? All right. So when we make these compounds, all right, we have to look at these groups as a whole. The charge comes with the entire group. Even though in this picture, right, these oxygens, at least the way I drew it, these oxygens have gained these extra electrons. It doesn't always stay that way. It's not as simple as this picture shows. This charge is sort of distributed among the entire group of atoms. They really do behave as a group, not as individual atoms. Okay? So the charge comes with the entire group, and that means we have to write the entire group. Okay? So here, let's go back to this. Okay? We know that this group of atoms, right, we call that the hydroxide ion, but they only get there because they got this extra electron from sodium, right? And so now, sodium's positive, this group of atoms is negative. What's going to happen here? They're going to attract each other, and they're going to form this compound. Oh, and they're going to form that combination of atoms. Okay? In that combination, everybody's got 8. Okay? We had to use a little bit of covalent bonding and a little bit of ionic bonding to get there, but everybody's got 8. Okay? Good? In this picture, right, this group of atoms, this chlorate ion, is now negatively charged. This sodium, because it lost an electron, is now positively charged. All right? We end up forming this compound. Again, every atom in that compound has 8 valence electrons. It just took a little while to get there, right? Combination of covalent and ionic bonding. Okay? Does that make sense? All right. Here, how many sodiums would this carbonate need to get itself to be 8 valence electrons for everybody? Needs 2, right? So in this case here, that compound would be one that we would form. Does that make sense? Okay. Jack, is that a question or are you stretching? Okay.
Can you use like 1 calcium?
You tell me. Could we use 1 calcium in this situation? Frank says yes. Why, Frank? It has 2 valence electrons. What is it looking to do with those 2 valence electrons? Get rid of them, right? So here, Jack, instead of this one, right, we could also make, okay, that's limestone, calcium carbonate. Yeah. You know when you get the water, like heat water, and it's kind of like got powdery sort of look to it. It's got calcium carbonate in it. No, it's not necessarily bad. Just kind of like chalky. All right, good there. So, along those same lines, let's go back here. Okay? Let's say that instead of this sodium, right? Go brown. Don't use brown very often. Calcium comes along, right? Frank, how many valence electrons does calcium have? 2, right? So it's looking to get rid of 2 electrons. It could transfer one of them right there, right? Now that hydroxide group is good, but is calcium done losing its valence electrons?
No.
What would it need? Another hydroxide, right? So the formula in this case has to include calcium and has to include hydroxide. But how many hydroxides do we need? 2. When we need more than one of something, what do we use to represent that in the formula? Subscript. Okay? But we can't do this. Okay? Because what is that telling you? It's 1 oxygen and 2 hydrogens, and that's not what it is. When we have a situation where we need more than 1 polyatomic ion, we put the polyatomic ion in parentheses to represent that we need more than 1 of them. Okay? Is that good? You okay with that? All right. So let's start doing some practice. Let's grab out that grid that I gave you this morning. All right. So I'm not going to do this in order because there's some rows that are easier than others. So first thing we need to do is we need to come up with symbols and especially charges, okay? So let's do the top part because there's all of your polyatomic ions, okay? Or your polyatomic anions. We just learned the symbol for hydroxide is what? OH, right? Yeah, I know.
You put them in either order.
Usually we put that oxygen first. That's just kind of how we write it. So, okay. Which is sort of contradictory to what we always do next because usually the oxygens come last, which is okay. But more importantly, or maybe not more importantly, but just as important, this is the symbol, but what charge does that hydroxide ion have? We wrote it down previously, right? How many electrons does it have to gain to get to everybody to 8? All right, so its charge is -1. We also talked about carbonate this morning. Carbonate is 1 carbon and 3 oxygens, but how many electrons did that carbonate atom have to gain to get everybody to where they needed to be? Do we remember? 2. So its charge is 2 minus. Okay. The other 3 should be on the list that are that chart that I gave you. All right. So I'll fill them in for you. Sulfate is SO4, so 1 sulfur and 4 oxygens. That combination brings us 2 electrons short of having everybody a stable octet, so SO4, 2 minus. Okay. Phosphate is PO4, 1 phosphorus, 4 oxygens. But it has a 3 minus charge. Right? Easy, everybody. Easy. He's grabbing some stuff for doing waves. That's all. Is the paper bag in there? Is there like a paper bag? Is like a Chipotle bag? I think yeah. So. No, those are empty bottles. And then nitrate is 1 nitrogen, 3 oxygens with -1 charge. Okay? So here it's not like I said, like the last 4 of them all end in 8, right? But some of them have 3 some of them have 3 oxygens, some of them have 4 oxygens. They all have different charges, so there is no real pattern there. That's why you kind of just have to memorize them. But I won't make you do that now. All right, 3rd row down is potassium, right? Find potassium on the periodic table. How many valence electrons does it have? 1. What is it looking to do with that valence electron? Lose it, right? And so, right? K, and then its charge will be what? 1 plus. Right? Okay. So now let's start putting the pieces together, right? 1 plus, 1 minus. How many of each do we need to make get everybody to where they need to be? 1 apiece, right? So here, KOH. Okay. Let's do formulas, then we'll do names, because names are kind of easy after that, all right? So, sulfate, 2 minus. It has to gain how many electrons? 2. Each potassium can only donate how many? 1. So how many potassiums do we need to get sulfate where it needs to be? 2, right? We show the 2 potassiums with the subscript, right? And then the sulfate comes after that, okay? We don't need extra sulfate groups here, so no parentheses, okay? We only use the parentheses when we need more than 1 polyatomic ion, right? Phosphate, 3 minus, right? Each potassium can only donate 1 electrons. How many potassiums are we going to need for each phosphate? Okay. Carbonate needs to pick up 2. Each potassium can only pick up 1. Alright? And then, on the end, right, what ratio are we going to end up with? What ratio from there to there? 1 to 1, right? Nitrate needs to gain 1 electron. Potassium needs to give up 1 electron. Potassium, nitrogen. Okay. All right, good there? So, names. Names are a little bit easier for polyatomic ions than they were even for the ionic compounds, right? All we do is put together the name of the cation with the name of the anion. The name of the anion doesn't change when we're dealing with polyatomic ions, all right? So the cation in this combination is what? Well, the cation for every single one of these is what? Potassium, right? That's the positively charged one, right? So all of these are going to start with potassium. And then the anion here is what? Hydroxide, because it's a polyatomic anion. So potassium hydroxide. Potassium sulfate. Potassium phosphate. Potassium carbonates. Potassium nitrates. All right, does that make sense?
Yeah.
Okay with those? So Jack, let's address your question from before, all right? Can polyatomic ions form with other polyatomic ions?
Yes.
And the answer is yes. Okay? So, all of the numbers across the top don't change. This is still hydroxide, sulfates 2 minus, 3 minus for phosphate, CO3 is 2 minus, nitrate is 1 minus. Right? Ammonium is one of the only polyatomic cations that are out there. There aren't many of them, but there are a few. Ammonium is one of them. The fact that it's a cation means it has what charge? Positive charge, right? Ammonium is NH4, but in order for that to happen, there actually has to be a loss of electrons, so it ends up with a positive charge. Yeah? I agree with you. It is actually. Especially because those are all nonmetals and they don't usually give away electrons, but that happens here. Yep. All right. So when we form when we make the formula, right? It's still cation first, anion second. It just so happens that the cation in this case is polyatomic, right? Ammonium has to give away 1 electron to get its positive charge. Hydroxide has to pick up 1 electron to get its negative charge. So what's the ratio going to be between ammonium and hydroxide? Does that make sense that it's just a 1-to-1 ratio? Yes? So, cation first, NH4. Anion second, OH. Now, you might say, well, wait a second. Hydrogen shows up twice in that formula. Shouldn't it be NOH5? Technically, that would give you the same number of atoms. But we use the polyatomic ions to more accurately represent how they're sort of joined together. Okay? So it's okay that we have hydrogen twice in that formula, even though, right, just because of the way that it lines up. All right? So, ammonium, +1, it has to lose 1 electron. Sulfate, -2, it had to gain 2 electrons. So how many ammoniums do we need for each sulfate? 2. When we need more than 1 polyatomic ion, we got to put parentheses around it, right? So, parentheses, NH4 is going inside the parentheses, but then a 2 after that. 2 subscript, right? And then sulfate ion comes after that. Okay? So in this formula, in this compound, I guess I should say, how many hydrogen atoms are there? There are 8 hydrogen atoms. Does that make sense? Right? Because each group has 4 and there's 2 groups. Right? Go ahead, fill the rest of the row in. Okay? Alright, does that make sense? Okay. Name-wise, name is just putting together the name of the cation with the name of the anion. So in this case, the cation is a polyatomic cation, but it doesn't change how we name something. So the name of this formula will be ammonium hydroxide. This is ammonium sulfate. Remember, we don't change the ending of the polyatomic ion.
How would it be like dry?
In this case here, just like when we were doing the ion, because remember, these are ionic compounds, even though they have nonmetals in them because of the transfer of electrons. There is no other combination of ammonium and sulfate that we can do. It's always going to be 2 ammoniums to 1 sulfate, so we just keep the 2 names there. Right? The prefixes only come in when we're dealing with covalent compounds. Nonmetals only covalently bonding. These are nonmetals, but they're ionically bonding because of the way that we trade electrons. All right, does that make sense? Good? You want to see the answers to the rest of the page? I don't know if some of you may have worked ahead or not, but you tell me. What's aluminum? Is it metal or non-metal? Yeah, but what is aluminum? Aluminum's a metal, right? Yeah. All right, so I'm going to put up all the answers to the rest of them up on the board if you would like to start working on them. We have a couple minutes before the end of the period, so should probably be able to get it done. Go ahead and work with the person next to you, and if you have questions, I'll be around. Okay? I would say, yeah, probably a good idea for you to try to do them yourself, right, before you look at the answers on the board. Feel free to talk to the people next to you if you have some issues. Not just to give them a hard time about something. So. Yeah. Alright, so I'm going to stop the recording right now, but tomorrow we'll start getting into properties.